So now here, what is the additional parameter which we are going to calculate after the my velocity propagation as well as the intrinsic impedance? That is nothing but the beta. Already we have studied in the network analysis that is gamma is equals to alpha plus j beta. Okay, gamma is equals to alpha plus j beta, and that gamma was your the propagation constant, alpha was attenuation constant, and your the beta was the phase constant. Similarly here we are interested to find out the value of the propagation constant, that is nothing but the beta, and that we can simplify with the help of the angular velocity, angular frequency, or divided by the vp, that is the velocity of propagations. Okay, so here will be beta is equals to omega divided by vp, and we know very well omega is a 2 pi f, and the vp already we know very well 1 by root of mu and the epsilon. So by substituting this value, you will find that is a propagation constant. So how we got this propagation constant? Okay, with the help of the these two equations. Okay, so C1, C2 are nothing but the constants. Okay, Z is nothing but the Cartesian value. T is with respect to the time period. Vp is nothing but the velocity of propagation. These we are writing the equation P1 and the P2 by focusing on the what we can say the twice, or you can say the voltage and the current equations. Yes, that is if once the my Z is a positive and the current is flowing that vertical, that time I can write my equation. That time the Z will be the positive. Similarly, in the second time my Z will be the negative. Likewise, I have written this equation. So here, if you are going to add the electric as well as the magnetic field equation in the x and the y, so you will be able to find after simplified in the previous case, that is Ex, that is already we are aware the electric field intensity was at the x position, and the magnetic field intensity was propagating in the y direction, and the Z was along with respect to the time period. So see here, already we have calculated beta is a propagation constant. Here the values after simplifying we received such equation. So here if you are interested in the angle, yes, definitely angle can be found, that you can say the phase angle or the instantaneous phase or the angle you may say, and we are aware this angle we can find because of that Z value, because that Z is nothing but the vertical, and that plays a major role. Okay, the electric and the magnetic field, even though that they are propagated in the x and the y, the other remaining part was nothing but your the Z. Okay, so that's why here the Z plays major role, and with respect to the time period, in this way we have calculated this thing, that is the instantaneous phase angle phi with respect to the Z and the T. So what will be my case? The case will be the how I got this. This will be the differences between the two parameters. Once again, if you have the plus Z and the minus Z. So in the first cases, omega T is nothing but again the 2 pi f. You may write here the f will be 1 by capital of T. Okay. So here beta you need to substitute the value of what you can say just now we written, that is nothing but omega by Vp, that you can substitute here. Okay, this is also for the lossless medium, how we can write the speed which is the constant value, and how my phase will be travel, that is nothing but the phase velocity. And if you are going to concentrate in the lossless medium, that time which will be equal and denoted by the velocity of propagation. So here the many formulas are mentioned which we have already done. This is the angle or instantaneous propagation. If you want to find out, you may take this one. Velocity of propagation you may take. If you are to deriving with respect to the differential equation, that time you can say, because we are aware that is a Z and the T is just with the what we can say the x and the y, that is electric and the magnetic. The remaining part was the Z only, and that too with respect to time period we have taken. So Vp is nothing but omega by beta, and by substituting the value, and they will cut out the common part. So finally you will get Vp is equals to 1 by root of mu and epsilon. So see here lambda now will come in the picture, that is nothing but the wavelength. Already we know very well the wavelength lambda is nothing but 2 pi by beta. Beta is nothing but the phase constant. Okay, and in the reverse order if you want to calculate, so this beta and the lambda will be equals to your the 2 pi. Okay, so in short you can say this is nothing but the distance of a long distance, and the direction of the propagation over which the instantaneous phase will be the changes by the 2 pi every time in the radians that is mentioned. So in short, lambda will be the wavelength which will be measured in the radians 2 pi by beta. So see here, this is the sinusoidal waveform. Okay, this is nothing with the upper portion we are treated as a Z already. We know bottom is again the minus Z. Here will be the plus Z, and here will be the minus Z, and these are the peaks of your the X and the Y. X will be your the electric field, and Y will be your the magnetic field. And this is my peak to peak, or the length or the distance between these two peaks is nothing but your my lambda. That is nothing but the wavelength. See here, the relationship between the wavelength and the frequency in the free space is mentioned. Okay, so this lambda, if we are talking about the free space, that time this lambda will be equals to, this C is nothing but the light, the natural light. Okay, so C by this F. Okay, again the relationship between the wavelength in the frequency. Okay, how we can write, if in many cases if you are having the light equation or mention the light, focusing on the light, that time you just use this formula. Otherwise you may use if propagation velocity is mentioned, that time you can use this wavelength formula. Similarly, if you are going to measure the phase constant in the radian per meter, this is the unit of the phase constant. Okay, because we are aware gamma is equals to alpha plus j beta, so that is a propagation constant that will be equals to attenuation constant plus j of phase constant. So here the we are interested in the phase constant, so that's why beta will be there, and that beta will be measured in the radian per meter. Okay, how I can simplify, there are various formulas. So see here, beta will be equals to omega divided by Vp, or if you're not using this formula, you can use this omega root of this term. These are just simply depending upon the numerical and whatever the things are mentioned in the numerical, as per that only you just make a changes in the formula, and you can continue which things are reducing, which things are common, which things are going to cut. Okay, so like this you can do it. So here the time harmonic analysis is nothing but the sinusoidal waveform, you can say, and that sinusoidal waveform are nothing but in the form of the steady state. That is nothing but, or you can say the time harmonic. The analysis in the form of the with respect to the time variant, and that too the wave is the sinusoidal. That is important because the wave may be the sawtooth, square, or other. So, but here we are focusing my wave is in the sinusoidal waveform. Okay, and with respect to time period, we are going to analyze. That time you can say the analysis is very useful in the electrical engineering point of view. Just because here mentioned the arbitrary waveform can be represented by the super position of the sinusoidal of a different equation. And also we know very well in the uniform plane wave, while you are going to simplify the numericals, only the so Maxwell equation is not sufficient. You may continue, you may analyze, you may simplify the numericals on the by using your the Fourier analysis. Okay, so in the Fourier analysis, again the Fourier series and the Fourier transform plays a major role, that is in the time domain as well as the frequency domain. Okay, time domain as well as the frequency domain. Remember, the Fourier analysis will be the Fourier series and the Fourier transform. So Fourier series and the transform, if you're talking, then definitely that will be the time domain and the frequency domain. So likewise, whatever we have done in the previous cases, same thing is here. Here the derivation part, that is right now there is no need of proof this equations is, it is in the cross and the dot products. See here, if possible, lossy medium, lossless, and here the lossy medium. So that time which things are important. So in this way, for today's session, I'm going to stop here. In the next session, we will continue to know the few numerical on the basis of what we can say uniform plane wave, plane waves, and whatever we have seen today, the theoretical part related to the intrinsic impedance, wave propagation, the phase constants, other parameter, we will simplify the numericals. Okay, so tomorrow session is important. So till that, stay safe. Thank you. I'm going to end this meeting.